Welcome to the Dork Forest. Jackie and her pals will never bore us. Shameless confessions
about our obsessions
will make us laugh and smile. So let's explore the Dork Forest and dork out for a while.
Hi, it's Jackie Cation. Welcome to the Dork Forest. It's the intro. This is where the credits and our monthly sponsor is mentioned. He's a good egg. It's Car D'Angelo over at Earth 2 Comics is sponsoring the Dork Forest this month. Earth 2 Comics is in Sherman Oaks. It's also in Northridge, California. And if you go into either one of those stores and you mention that you are a ranger of the Dork Forest, you will get 10% off your purchases. Very exciting. Today is October 8th. And tonight is the Walking Dead party that starts super late because it's October, and October is spooky month. I love Earth 2. Very, very supportive staff. They can help you find stuff. If you don't know what to get, you can sort of describe the kind of things that you like to read. And I don't know, if you go to the Sherman Oaks one, they might even tell you what Maya and Andy's pull list is. And then you can know more than you need to know about what kind of comic books to get. But Earth 2, super friendly staff. And they have everything. And if they don't have something in one store, they will send away to the other store and hook you up. And I recommend that you all go there. And I recommend that you mention the Dork Forest because then you get 10% off. There's the ad. In other news, JackieCation.com, DorkForest.com, TheDorkForest.com, AllThingsComedy.com is the podcast network that the Dork Forest is on. And there's a lot of great podcasts over there. If you're looking for more pods, there you go. My stand-up and live Dork Forests are on JackieCation.com. There's a chance to buy merch. There's a chance to go to the Amazon banner and buy whatever you want from Amazon, and I get a kickback. The Dork Forest gets a kickback. And other than that, there's T-shirts and CDs and the calendar. Oh, and the donation button, of course. Everyone should give me $100 a year. Do what you can. If you have to give it to me in $4 increments, you're going to have to do the math because I don't know how to set that up. I've asked Mark Maron. He's told me twice. I still haven't done it. Anyway, let's get into the show. It's a good one. Hey, it's Jackie Cation. Welcome to the Dork Forest. Sitting with me, finally, Robert Hurt, space scientist artist guy.
Hi, Jackie. It is a delight to be here. And of course, it's Dr. Hurt to you.
Oh, that's right. PhD in English? No. Such a jackass. Anyway, what is it what is your
PhD in astrophysics.
Jesus H. Christ, you're a rocket scientist.
I'm a scientist whose science happens to happen on things that got launched by rockets, which is subtle but different than being a rocket scientist.
It is. But you know the science of rockets.
I can fake it at a cocktail party. Yeah.
Right, sure. And at one time you studied the science of rockets. Is that what Astrophysicist is?
No. We study everything else.
What do you mean?
Well, once you get past the Earth, everything.
Right.
Everything.
You mean the wallpaper that's up in the sky that doesn't have any aliens because of the...
Bingo. Yes. Stars, planets, galaxies, cosmic microwave background. Yeah, it's all, so, everything that you don't get at a liberal arts class, everything that's outside of us is,
right.
So really, we have the bigger slice of the pie to play with.
Fair enough. So now, there are so many things I've been trying to get you on the show for approximately 7 years.
Yes.
And, there can be anything. You are known amongst your circle, which Andy Ashcraft is one of, for these many years, that you taped all of the Next Treks, Star Trek Next Generations.
Oh, of course, yes.
And then edited all the commercials out.
Yes.
And this is all on VHS.
And everyone always came over to my place for it.
It was a social moment.
It was a social moment.
You and 70 of your closest friends, which you continue to have.
It is literally true that for the season premiere of the Best of Both Worlds Part 2,
Sure.
Fire! He is a Borg. That's right. I had a little one-bedroom apartment and 35 people crammed into my living room to watch it must have been 12-inch TV set or something at that point.
That's awesome. I love that, though, because that means that we all like each other, because we're willing to go shoulder to shoulder. What I didn't tell you is that my phone rings usually during the episode. It's usually not minute 2. But, Okay, so you could talk amongst yourselves.
I'll assume we'll edit this part out.
No.
Oh, no.
No.
That's even more exciting. Well, I should turn my ringer on then, because it'll even add more excitement if my
Rangers
phone
of the
rings.
Dork Forest are aware that a lot of things are happening. You've been offered some Dove dark chocolates. There's some cashews that have nuts in them.
And York peppermint patty.
And York peppermint patties, which are kind of glamorous, as we are here in October, the time of candy. And so Andy's candy purchasing broadens somewhat. Usually it's just some sort of dark chocolate business and the cashews. But clearly he's lost his mind. We have Reese's peanut butter cups and York peppermint patties and
the
flan.
insanity of it.
It feels insane. How I deal with it is I tell myself, it's not my candy. It's his candy. You don't get to touch it. It's his candy.
Yeah. If it's not dark, I'm not interested anyway. So.
Well, it's right.
Chocolate
I don't think it is a dark chocolate York. I think that they used to have. This is a fascinating tale. I have better things to talk about with you. Okay.
The universe, everything.
Exactly. Number 42. Okay. So do you work for Caltech, JPL, or NASA?
Yes.
Okay.
Because
in that order?
Something like that. I work on the Spitzer Space Telescope mission, which is one of NASA's 4 great observatory projects, the cousin to the Hubble Space Telescope.
Right.
The infrared part of the spectrum is what we deal with. And JPL is Jet Propulsion Labs, is a NASA facility that is managed by Caltech for NASA.
Okay.
So NASA gives Caltech a big check, and then they go run JPL, which then writes a check and hands it back to Caltech that pays me to work on the Spitzer mission that they do.
Right. And what you do...
And it took a PhD to understand that, actually, and about 5 years.
And you've been working there for a while, right? At least 10 years, or
yeah. I've been working actually at the facility, the Infrared Processing and Analysis Center, now for since like 97, 96.
Okay.
Postdoc for a couple of years. Worked on the 2-micron all sky survey, which was a ground-based infrared mission that made the first high-resolution digital map of the entire sky from the ground. And
wow!
And so I worked on that as a quality assurance scientist. And then as we geared up for Spitzer, that was going to be the next big observatory project coming through, they basically created a job for me because on 2MASS I'd already gotten a reputation of being really good at taking our data sets and turning those into really nice imagery, to visualizing the data very effectively. Because
right. Whenever I tell people, I simplify what you do, which belittles the 20 years of work you've put in. But what I like to do is I like to say, he makes art out of the pictures in the sky.
Hey, that works.
which is what you do. I mean, when someone sees, this is what the Milky Way looks like from the Spitzer. This is what this image looks like. This is an image from the Spitzer. It's been colored, it's been cleaned up. It's been cleaned up in many, many ways, right?
Right.
So you get raw data.
Right.
What does the raw data look like? I mean,
like any telescope.
There's a telescope where is the Spitzer?
Okay,
what
first
is
of all,
the Spitzer?
Spitzer it's an infrared telescope. So to do infrared light properly, you actually need to be very, very cold because, everything emits light. I mean, you emit light. I emit light. But we emit it in the infrared. You glow. You do. And if I had our 10-micron camera, I could take a picture and show you that you were positively glowing. You're hot. But because of that, trying to take a picture in the infrared using a warm camera is like trying to take a photograph when you open up the back of the camera and let light flood in, right? The camera itself is emitting the same light that you're trying to actually take a picture of.
Right.
So what you have to do is you have to cool the entire camera down to be a lot colder than the thing that you're actually trying to photograph.
Okay.
And so
that it isn't registering.
Right.
So you're taking a picture of the only heat and light that there is.
Right.
Okay.
So in order to do that, a couple ways you can do it. You can take the whole telescope and stick it in a bath of like liquid helium.
Okay.
Or the way Spitzer was designed was you take a telescope and you design it in such a way that if you kick it away from the Earth, because the Earth is also very warm, Earth radiates a lot of heat, and it warms up in the sun and everything. By pushing Spitzer away from Earth, we actually kicked it off into its own orbit around the sun. And so it's sort of slowly falling behind the Earth, as it cycles around and around the sun. And right now, Spitzer is actually further away from the Earth than we are from the sun, just sort of back along the Earth's orbit.
Okay, so is it following the Earth's orbit, or is it on its own orbit in sort of an oblong kind of way, so it will eventually hit Pluto and then out be in the world.
It's in a circular, more or less circular orbit like the Earth, just a slightly larger one.
Okay.
So it takes a little longer than a year to go around.
Okay.
So from our point of view, from our very Earth-centered point of view, we call it an Earth trailing orbit because we just see it trailing, drifting further and further away from us over time.
Okay.
And as a result, though, that just means all we need is one sun shield to protect Spitzer from the sun, and we have solar panels on that to generate electricity. And then the other part of the telescope, the outfacing part, is actually painted black, and black radiates heat very effectively into space. So the Spitzer acts like this little mini heat pump. The part that's facing the sun warms up, and it's all like thermally insulated from the telescope, electronics, and that's all thermally insulated from the telescope. But the telescope, it basically just dumps its heat off into space. And even without any coolant, Spitzer sits around 30 degrees above absolute zero.
Okay.
And then when we had coolant, we actually could cool it down as much to like 4 or so degrees above absolute zero.
Right.
We ran out of coolant about 5.5 years in the mission, but there's still one instrument that actually continues to work.
Is
because
it being
that can
remotely can you affect it remotely?
Well, it's not like, a little Wii controller or anything, but it's like we do daily uplinks to it and basically give it its next set of instructions of which things we want to observe.
Right, and you have to be able to download stuff. It has to transmit the images that it gets, right?
Right, exactly.
Okay.
And our limiting factor these days is more the downlink speed because it's so far away from the Earth now. The data rate actually is a lot lower now than it was 5 years ago.
Okay.
So it's we're moving more in towards like trying to get our data down over like an old audio modem rather than through a DSL connection.
Okay.
But it's still collecting wonderful data sets in a couple of the wave bands. But then what we get back from it, of course, is all infrared detectors. All detectors really are, you effectively get a single grayscale image. You put a filter in front, or you have a detector that's built to work with a particular range of wavelengths of light.
So it doesn't look like very simple. Jackie Cation, not a science lady. Predator. That's what I think of when I think of infrared. What am I not?
The Predator. Well, so
the Predator movie.
The Predator movie does a great job of kind of introducing people to this idea because what happened in Predator, right?
Yeah.
The idea of the thermal emission. Yeah. They're basically getting a grayscale image of light and dark, things that are bright and faint. Because the Predator vision is really only working at sort of one band of light. Yeah. But to make it more visually interesting, instead of just showing it as a black and white Woody Allen picture, right?
The Annie Hall version.
The Annie Hall version of Predator, right? They just went ahead and applied a gradient of color to it, so that the stuff that's black maybe was still dark, right? And then the gray stuff was purple, and it went on up to yellow and blue and this multispectral. And so that's what they did was an act of visualization, because they found a way to transform this simple grayscale data into some kind of colorful thing that you could then maybe get excited about or interpret.
Right. Which is what you do.
Which is what I do, yes.
Okay. So what I have is how to go from data to picture is what we're in the middle of, right?
Right. And
then visible light versus the rest of the spectrum. Have we talked about that?
Not really, but we can certainly do that.
Let's touch briefly on it, just because the infrared being non-visible light, right? Or
so the thing, I guess, one cool thing about light that I think people don't really appreciate. We're very egocentric, and we think of light as yellow and blue and green, and that's it, right? If it's not visible, it's not light. But
it's sunlight. It's sunny.
But the sun emits a hell of a lot more than visible light. Now, it's brightest in the visible part of the spectrum, but it actually emits light across ultraviolet, right? Our sunburn rays, it's warm, it emits infrared, it even emits a little bit of microwave and radio family. Okay. And what's interesting is there's really nothing fundamentally different about X-rays or ultraviolet or visible light or infrared. It's just what we call electromagnetic radiation. It's just waves. It's just waves of electric and magnetic fields. The only thing that's different between an X-ray and green is that X-rays have a much shorter wavelength.
And
the fields are spaced more closely.
See them.
And our eyes can't see them. In fact, it goes right through our eyes, actually. So it's like nothing doesn't stop to detect it. We just biologically, over billions of years, because our sun is actually brightest around a range of 400 to 800 nanometers.
Okay.
guess what? That's where biology found let's evolve little detectors that work best in that part of the spectrum.
Okay.
And so our bias of what we count as visible is a pure consequence of natural evolution, evolving light detectors that are going to work in the part of the spectrum where there's more light to work with.
Okay.
If we were
It offered us that light, and that's the way we evolved to make use of that light.
Exactly.
Okay.
Now here's the dirty secret of Superman, I think.
Oh.
Because
Welcome to the Dork
Because we all know that Superman comes from Krypton, which orbits a red star, right?
Oh, right. Yes.
And Krypton's sun, as a red star, a cooler star, probably emits most of its light in the infrared.
Okay.
Because the reason the star would look red is that its spectrum is dropping off quickly in the visible, which means it's probably peaking once you go into the infrared, which means that probably Superman and all Kryptonians would actually see infrared light, not what we think of as visible light.
Okay.
And-
or X-ray?
Or, no, not, well, they wouldn't have it evolved to see it. See, they wouldn't see X-ray at all because X-rays, there'd be almost no X-rays coming out of their sun. No, even hardly any ultraviolet.
So what about on this planet, though?
So Superman really ought to have had infrared vision, not X-ray vision.
Right.
Biologically, evolutionarily, Superman doesn't make a lot of sense.
And I'll tell you something. Another mistake, DC. Stop micromanaging things. Anyway, but by pushing to these longer wavelengths in the infrared, the reason we built a telescope is that every color of the spectrum tells you something different about what's going on. Visible light, we see things that are actually really, really hot, things like the sun. Okay.
Sun's like 5,000 degrees.
Okay.
And that means it peaks in the visible part of the spectrum. Things that are just 1,000 degrees or hundreds of degrees, they put most of their light out in the infrared. So the infrared lets us actually see things that are cool in the universe instead of things that are hot.
Oh.
And cool things which are also pretty cool,
right.
are like the vast clouds of dust that fill the galaxy and the cocoons of dust that stars and planets form inside of.
So space, another very basic question, not empty.
Space is not empty. It's not, again, our visible bias that we see in visible light, just the hot things, those pinpricks of stars in the night sky, kind of bias us to think of the whole universe as an empty space with just a few little pinpricks in it. But in fact, if we naturally saw infrared and we looked out in the sky, it would be just filled with glowing dust and clouds and everything just vivid. There's a tremendous amount of interesting stuff going on between the stars as well.
Right. So, and I'm sure, but it would be distracting if it were between here and the atmosphere. Like if we could see infrared and we just looked out the window, it would be very busy. Am I correct?
It would. There's, in
Possibly
fact, that's
busy.
why we throw them into space, our telescopes, because our atmosphere actually, there are few narrow bands of infrared that actually make it through our atmosphere. We build telescopes that see.
Okay.
And, like the 2 micron sky survey worked at bands out to about 2 microns. But once you get past 2-3 microns, our atmosphere is mostly opaque until you start getting out into the radio and then the millimeter waves, and then it starts coming through. So for those bands, though, our atmosphere just totally blocks it. So that's why we put telescopes in space, so they have a nice clear view of it.
Okay. Wow. All right. So how long has the Spitzer been out there?
Spitzer launched in August of 2003, and so we actually just had our 10th anniversary celebration.
Yeah.
And a big party
10
at
years.
once. 10 years. Okay.
So, now what I was given is hated words, hated terms. This is, my last episode was with James Adomian, stand-up comedian, very funny man, a bit of a conspiracy theorist. And he says to me, that's pejorative, conspiracy theorist. So, we changed that to a guy that has some info. I don't know what we changed it to, but so you don't like colorize. I don't even like colorization. So
exactly,
colorize and false color. What does that mean?
So getting back to your original questions were about how do we visualize these images, right? We collect this data. It's intrinsically sort of black and white.
It is in the
data.
Woody Allen kind of.
It is in the Woody Allen, but we can collect it at different bands of the spectrum, right? We have the Spitzer had one detector that worked in the near infrared wavelengths that had 4 different wavelengths it detected. It had a different imager that did 3 longer wavelength bands.
Okay.
So but what we get is a single band of data in sort of grayscale brightness once we grid it up and plot it out. And what we have to do though is we want to make imagery. We want to combine as much of that data together as we can. Now, our eyes see 3 bands of light that we piece together to see all the colors that we see.
Okay.
Red, green, and blue.
Okay.
You know, you go up your TV set and you take a magnifying glass to it. You only see 3 kinds of pixels on it. There's red, green, and blue phosphors.
Oh, and then they mix to make the other colors.
And they mix to make all the other
Okay.
colors.
I remember
Everything's
that.
proportional. It's, you know, if you work with computers at all, you know, your data, your Photoshop documents have a red channel, a green channel, a blue. And when you assemble them all together, you get all the colors.
Okay.
So we can, now, of course, your camera does the same thing. It actually has detectors that have little filters detecting red and green and blue, and it puts it together and you get a color image.
Okay.
Well, it just does that all behind the scenes, and so you don't really think about it. We always take the red light and we show it as red, and the green light we show it as green, like that.
Yeah.
We don't have to, though. I mean, it's computers. You can mix things up.
Right.
So what we do, of course, to visualize colors beyond our ability to see is to take different bands outside, say, the visible spectrum, but then bring them back in and assign them to red, green, and blue for display.
Okay.
So the colors, we generate color images, and the colors are real. They're just not the same colors that we see.
Okay.
I mean,
we would see.
Or that we would see, right.
Okay.
You know, if I showed you an actual true color infrared image, it would look blank. Because you can't see infrared. So that showing you the actual infrared the way it looks would do you no good.
So when the infrared images come in from the Spitzer, they come on a gray scale.
Yes.
Okay. And
then we
they're
make
assigned
choices.
Different wavelengths or
So we know it comes in at different wavelengths, like
right.
3.6, 4.5, 8, 24, whatever. We pick which ones we want to emphasize, which one maybe have the interesting science that we're trying to do, or
right.
have good, interesting features that are different at one band than another. Then we reslot them into red, green, and blue to bring out a color representation of what it really looks like in the infrared.
Right. So if you want to show like the rings around Saturn or something, could we see the rings around Saturn?
Well, actually, Saturn is actually so blindingly bright to Spitzer. Spitzer is so sensitive. We can't even point it at the planets. Though, interestingly, one of Spitzer's really coolest discoveries over the last 10 years was Spitzer actually discovered a new ring of Saturn we didn't know about. Its largest ring. There's this huge ring around Saturn that actually goes out as far as some of its outer moons. And it only can be seen in the infrared because it's made of very fine dust particles.
Oh, wow.
And so we'd actually position the camera off of Saturn. You know, it was sort of glaring off to the side.
Yeah.
And this band, just showed up in the frame. And then they reconstructed it. It actually is thought to be tied to the outer moon Phoebe that probably kicks up dust when things hit it.
Okay.
It actually explains why the moon Enceladus has like a dark side, because the dark side is probably where it's sweeping up material from this otherwise invisible ring that you have to go in the infrared to see.
Oh, that's so cool.
Sorry, side note.
No, because I wonder about what have you, because so somebody tells you the science. They're like, we want to point out that we found this new ring and it's made out of this super fine material, which is why I came up on this infrared. And so we need you, Robert Hurt, to emphasize that by picking the colors that would best show that. Is that correct?
Right.
Okay. What's another thing that you've what's another science thing that you've pointed out, I guess, is a very basic question.
Well, so what's interesting is so my job is fun because it's half scientist, half photographer. Because what's interesting about the way the data comes down is it has this full dynamic range, right? I mean, you take a photo, you have to actually choose, how are you setting the exposure on it? Am I exposing for the dark part or the light part? And you'll only get part of the image, you know?
Yeah.
The window if I took a picture in this room of you, everything outside would be totally blown out because you can't see it.
Right.
Well, astronomical data actually comes in with much higher dynamic range. So the first thing we almost have to do is just decide what's the exposure? What part of the image are we bringing in? Okay. And there are actually ways that we can compress the dynamic range of the whole image so you can actually see both the faint stuff and the bright stuff, which pushes in a kind of non-linear realm that's different than what we're used to in just, a snap and click photo.
Perspective-wise? Or?
No, just... there's actually a kind of photography that's more popular even now called HDR photography, high dynamic range.
Okay.
Where you might take a whole series of exposures at different exposure settings.
Yeah.
And then combine them to a single image and then reprocess it in a way that you can see both the darks and the lights. Okay. This is very popular now in traditional photography But astronomers have actually been doing this for decades now. That's actually kind of part and parcel of what we do.
Okay.
And so, so part of it is looking at the data and deciding, what's the full dynamic range of the image? Do we have to kind of place mathematical calculation on top of it to kind of scrunch it down so we can see the bright stuff and the faint stuff? What's the interesting part of the image?
Yeah.
Then we take the different channels that we've observed and assign them into colors like red and green and blue. And then we sort of want to choose which bands of light go into which colors. Then we end up producing a color image.
Yeah.
Now, historically, this kind of imagery has been called false color imaging.
Because essentially you're creating color where there was none? Is that what the implication is?
That's the problem. That's what it sounds like. It sounds like you're creating color where there was none. I mean, when you think, false testimony, you think something is a lie, right?
Right.
False witness, someone isn't really saying the right thing. False is a bad word because it's loaded with this idea that there's something
that you're
conspiracy,
cheating. Right.
A conspiracy
right,
to hide what's going on, right?
Talk about pejorative.
Exactly. So, but the term was innocuously created to try to set apart the idea. Again, in the 70s when this term first surfaced, all we did was the way we made color images is just make red, green, and blue as red, green, and blue. We put photographic film in a telescope, and we got a color image out. Oh. And there was this need when we first started pushing into different parts of the spectrum or processing it differently to make sure people didn't think this was the actual red, green, blue color of something. So the term false color came up to say as a little warning, this is actually a different way of looking at something.
Just to be aware of
it.
Right.
Now, of course, all of astronomy is false color today. I mean, there's almost no astronomy ever done in red, green, blue.
Okay.
Even the stuff that's done in visible light usually uses very narrow little filters around certain features that say hydrogen gas puts out or silicon or carbon, and then we recombine it in a way that would not be the color your eye would see anyway.
Okay.
So to call the entire field of astronomical visualization false color,
we don't. Seems like a punch in the throat for no reason.
It does, and everybody,
What's
all my
colleagues,
all my colleagues who did the same thing for Hubble and for the Chandra X-ray Observatory, for European, so we get together occasionally for meetings and trade secrets and tips and tricks, and we all hate false color, and we're lobbying to get people to really just describe it for what it is instead of saying it's a false color image. Say it's an infrared color image or a representation of infrared data.
Yeah.
A term I particularly like is translated color.
I like translated color.
I mean, if I show you,
that's exactly what you're doing.
Well, exactly. If I show you a copy of The Art of War in the original Chinese, it means nothing to you. But if I show it to you in English, you're like, oh, okay. That's in English. It's a translation. It's not a false copy of the book.
Right.
It's a translation.
Right. It's you are now able to comprehend the book that was in Chinese.
Exactly. And so that's exactly what we're doing with color. We're translating it from a different part of the spectrum. It's real color.
Yeah.
It's really there. If your eye actually worked in that spectrum, you would be able to see that variation.
Right.
But it's been translated into something that you can see.
Right. And now you can see it, and now you can understand the science, and you can understand the math, and you can and
appreciate the beauty.
And appreciate the beauty of it. That is one of the, is there a website where a lot of your images, like if people wanted to scroll through some of the images that you've worked with?
Yes, actually, in fact, there's been a really intriguing project that, again, the kind of the visualization community I'm involved with has been working on for many years. We actually have a website that's kind of in a beta form now called Astropix. Astropix.ipac.caltech.edu.
I will link that.
Link it, yes.
Is it PICS?
PIX.
PIX, Astropix.
Right. And what we've done on this site is a lot of the key observatories right now, the Spitzer, Hubble, Chandra, the European Southern Observatory, we have all been taking our imagery, the ones that we've really prettied up and released, we've translated into really nice, clean, public-friendly images.
Okay.
It has all this extra information, wavelengths and which telescopes went to which colors and what part of the sky it's in, all this.
Yeah.
We've folded this into a metadata format. Metadata, that's a... Yeah.
Well, it sounds important.
Play with. And we basically embed the descriptive information in the image.
Okay.
And then they all feed their assets into one location. And so we now have this new Astropic's website that aggregates all of the imagery all the public imagery that's been released from these different telescopes into one site, so you can find it all without having to go and search, like
what did Hubble see when it pointed itself at that part of the sky?
Exactly.
Okay.
So we've got now close to 4,000 images there from over a dozen telescopes.
Okay.
And not everything gets tagged at the same depth, but some of the ones that have been tagged most deeply, you actually get little widgets that show you how far away the object is, a little graphical thing that kind of gives you a hint of, is it in the Milky Way or in the nearby universe? We actually have one of my favorite features, apropos to this conversation, is that if it's been fully tagged with the color representations in the image, you get a little spectrum and little color indicators showing what color of the image is pointing to what part of the spectrum.
Oh.
And so you can actually look at each image. It gives you a translator's guide to what the colors actually mean.
That's awesome. Like a key. Like a map key.
Like a map key, exactly, to color.
Oh, cool.
And this is I think, this is what's so interesting about what's happened to astronomy in the last couple decades. Because, when I was a kid, all the astronomy images pretty much looked the same because they were all done red, green, blue is red, green, blue. We just worked in the visible spectrum. So nebula kind of glowed red. Dust clouds that had diffuse scattered light all looked blue.
Yeah.
Stars, galaxies were all kind of whitish.
Yeah.
There was a very common palette because that was the visible palette. But with the advent of multi-wavelength astronomy through the 80s and 90s and beyond, what happened was our palette began to change, because as you start looking at different slices, the way light combines from different parts, you get a different kind of color palette. So today, every kind of mission has its own palette of color that goes with it. Spitzer has a couple of very specific palettes we use, because I tend to use the same mappings over and over again for the same data combinations. I'll assign them to the same colors. So you will see this kind of color that appears again and again.
That makes so much sense, because then, it's like when Apple says that things are intuitive.
Right.
But they're only intuitive if you use them often enough.
Exactly.
And then you switch to a different device that has that same operating system or that same kind of interface. So if you're using the same color palette for the same kind of data, like that's a dust cloud, it's going to be sort of a yellowish white.
Right.
And then you go to it, you point it at the sky in a different place, and there's a dust cloud over there, and you can use yellowish white over there too.
Right.
And then if I looked at those images enough, I could go, oh, that's probably a dust cloud.
And that's exactly what happens with the scientists who work with it too. And
cool.
One of the more enjoyable parts of my job is the fact that I have more powerful tools, i.e. Photoshop,
right?
for actually building these color representations of the data sets than what typically exists in science analysis tools. The one area where I think astronomy is really, really lagging analytically is data visualization, because we have incredibly the visualization tools for just creating color imagery that are used in science analysis. They have not changed the way you manipulate color and contrast in over 20 years. They haven't. You don't even have a levels adjustment. Okay, you don't even have a levels adjustment in astronomy per se, and the metaphor is work. And in fact,
would that be on the Spitzer, the levels adjustment?
No, I mean in the tools that you use once you have the data set and you're analyzing it. I mean, you have this incredibly ancient way of doing this that doesn't let scientists generally create. They can't easily explore the subtleties of really just tweaking very comfortably and casually a little bit of the data set to bring out these intrinsic hues. And so when you really can dig in the data set and you know what's in the science, right, and you're trying and you can adjust it, you can be very, very subtle with how you do the colors. And so the actual even very subtle differences in color tell you something about what's going on.
The density but what do you look like are you talking about like the density or the
right? Well, it's the density and the proportions.
Okay.
I mean, there are areas like there's this beautiful nebula NGC 1999 or 1399 that is a region where there are a lot of baby stars, and when baby stars are in the later stage of forming, they tend to spray out what we call bipolar jets. Material that's kind of like blown out of the top and upper and lower axes of the stars, like the spinning disk.
Yeah.
Kind of like blows balloons into the space off on either side. And that's one way we can trace where the stars are. Sometimes, especially in visible light, you can sometimes see those jets, even though you can't see the protostars. But you can trace back They must be pointing. You can start to figure out where the pulsar must have been because you know where the jets are pointing.
Got it.
Now, in infrared light, we can actually see through the dust to the protostars, because that's the other thing you get with infrared.
Right.
As the wavelengths of light get longer, they are actually the light itself, the wavelength starts to get larger than the size of the dust particles.
Okay.
And so the dust particles don't really obstruct it so much anymore, and it passes through. So we can see into these clouds that you can't see in visible light. But when you look at a region like that, these jets, they glow for one set of physical reasons. There's an impact going on between material being sprayed up from the star as it impacts the other dust and gas around it, causing it to sort of light up as it stimulates different molecules to re-emit light.
Okay.
So that has a particular color to it. The dust itself is actually becoming visible in part because it's reflecting light from the nearby starlight as well. That takes on a kind of different hue. And when you actually can go in there and adjust it really correctly, you can actually tell the difference between the aquamarine dust and the yellow-green bubbles.
Right.
And then there's like the reddish dust that's actually fluorescing under a different kind of illumination. But these kind of subtle things are actually very hard to bring out in the analysis software, but I can do imagery that I can show back to the investigators, and then they can use the color to help them see more of what they're doing.
So there's analysis software that they're trying to work with as scientists, and there is Photoshop, which is what you're working in?
Right.
So nobody's written better analysis software that matches Photoshop.
Right. I mean, there are some really basic concepts in Photoshop, a curves adjustment, gamma adjustment. We don't have a gamma adjustment in any of the core analysis tools like DS9 or IRAP. It's not there. It's very simplistic. That could easily be added to this software. Right. And we actually developed a program, the sort of the astronomy visualization people. We actually kind of collaborated, and the kind folks out in Garching, Germany, actually brought in a team to program something what we call the Photoshop FITS Liberator. FITS is the data format the astronomy data comes in. Okay. And so way back in the day, we figured we needed a piece of code that would let us liberate the picture from that archaic format that's hard to actually see. And,
so you could transfer it.
So we transfer it. We create it into a FITS
Liberator
format. Yes, we liberate it into a TIFF file that anyone can then read. And part of that was we came up with very flexible algorithms for how we do this dynamic range stretch I was telling. Instead of just there are ways you can adjust and rescale, and you get incredibly subtle control over do you want 1,000 to 1 dynamic range or to really bring out the faint features as well. It lets us do something that's much more sophisticated than what a research astronomer can do with their tools. Mm-hmm. And it would be really easy to fold this back in. But it's like we haven't had a lot of good communication, I think, from the visualization community and the research community to really build sort of the next generation of tools. And we're looking to improve that in the future too.
And would there have to be sort of a relearning? But you'd think scientists, well, that's not true. I've used Photoshop so very basically that maybe there would have to be retraining of the scientist for that analytic, for them to use an updated software set.
It's always true. And scientists, astronomers can be a surprisingly Luddite group when you get around to it. For people that hidebound. Breathe, eat, and sleep computers to do their analysis, there is a surprising resistance to change as well. But that's in part because you're so stressed out and so busy, investing time to learn a new process is tough. You're trying to get that paper out.
Right. You're trying to get that paper out, and you're also looking into space, and you're like, it'll be fine. I'll figure it out on this thing. And I get that, but it would be, if they took a month or a week or even 8 hours to learn this new software that doesn't exist,
right.
It would probably make your job it would make their job, I think, easier, right?
It would. And more fun. I mean, the other thing is just we really have to improve the GUIs on astronomical software. It's just so
right.
We're very command line kind of crew,
Right.
Unix
Right.
type, right? And I still have a lot of colleagues who actually use things like Pine for any of your Unix and VMS geeks out there might recognize to read their email. Command line email utilities. It's
my gosh.
Yeah.
I had Lee Bennett on the show talking DC Comics. A lot of Green Lantern talk. And he when I picked him up, or I think I met him for dinner to talk about doing the show, he was like, well, do you want to see my work? And I was like, yeah. And he took me into a very cold room with a bunch of computers in it. And I was like, dude, what else is there? Show me something. I mean, it's neat. I mean, I love computers.
So a petabyte of spinning disk just does not excite you very much, does it?
Well, when he told me it was a petabyte, I was excited. I'm not going to lie to you. I think it was cool.
Yeah.
But it was very funny that he was like, see all these computers? Look how cool they are.
Yeah, well, the part that you need to remember is cool is that you can go in through, anyone can log in, actually you don't even log in. You just go to a web page and you say, there's this galaxy I want to look at, like M83, and you type in the galaxy and I'm
doing this. What is the website?
ursa.ipac.caltech.edu. I warn you, it's a little IRSA.
IRSA, okay.
The Infrared Science Archive. Ursa. Okay. And
so I could Google Infrared Science Archive.
You can.
And then that edu would come up probably.
Exactly.
There we go.
And you can go in. It's an astronomer interface, so it's a little clumsy, but it's not that hard to figure out. But you can actually call up imagery from visible light, from infrared, from Spitzer, from Herschel, from
all of them?
the WISE, from all of them. The 2 micron all sky cert, right? It's all there, and you can get.
What's a good looking galaxy? What should I type in?
Well,
what's one of your favorites?
Well, certainly today, M83 is one of my favorites.
Okay.
It's a beautiful spiral galaxy, but to connect it back to imagery for a moment, I gotta say, so last night I went to the M83 concert.
Oh, did you?
What is that? Wonderful electronica artist. He has.
Is that a band?
It's a band.
Okay.
Yeah, and
named after the M83.
Named after. He's actually a French electronica artist based here in LA, but his band is named after the galaxy Messier 83. I verified that.
That is a dude that is deep in the dork forest. He's got his own tree.
Oh, he absolutely
building a tree house.
He Hurry Up We're Dreaming is his latest album.
Okay.
Midnight City is like a big hit, everyone knows. But he also got tapped to do the score for Oblivion. The big Tom Cruise movie earlier this summer, which actually one of my favorite scores of the summer.
Okay.
Awesome going to the concert. Sit down. The second song comes up. Backdrop pops in. I did that image.
Did you do that image?
He used like 4 different Spitzer images as backdrops for songs through the course of at least 4. Several other, some Hubble things got in there too.
Had you done most of them?
And I definitely had done 3 of them, and one was a collaborative one that was a great observatory image. And I was just
yes,
freaking out all night long, because not only was he using this imagery, each image was then setting the color theme for the light show for each song.
Oh.
That's the Spitzer Galactic Center image, and it's like got all those lovely blues and reds. It's like, oh my god, this is so cool.
It really is.
So and that for me is the ultimate success, when the imagery that we put out there to help communicate and enthuse people about science can permeate into popular culture to the point that it's like the glowing backdrop at the Hollywood Bowl that thousands of people are looking at.
Yeah.
And it's, that's when we can really stimulate that kind of excitement and enthusiasm. And I can count as a personal success, because Hubble is so well known. Hubble has hit, pop culture, one side to the other.
It is the reference.
But there's so much more than Hubble that works out. There's a whole spectrum out there, and Hubble only sees a part of it. Mm-hmm. I am just astoundingly gratified to see that M83 is
aware of the Spitzer work.
Is aware of the Spitzer work and the spectrum. So I was just floating off somewhere near Alpha Centauri last night.
Do you get photo credit? Is there photo credit on those things? No. It's because it comes out of the Spitzer. Because it comes out of the production of the
and they play around. They put some warps and twists in to make it a little. So I was like, I knew it though. It's like,
You could
I don't
see it.
fuss. I mean, after I fuss with those pixels for a while, right? It's like, yes, I would recognize that galactic center anywhere, even if you did apply a Photoshop pinch filter and a little bit of rotate to make it a little stylish on the background.
Yeah.
Get some curves that match the
Right.
curves of the Hollywood Bowl.
Sure, of course. Why wouldn't you make it nice? It's okay. So before I really want to talk about these last two, but you mentioned Oblivion. What do you think of the Gravity business? The movie Gravity. Have you? I love Sandra Bullock, but I don't think I can see it.
I don't know. Is that out yet?
Yeah, I think it comes out this weekend.
Okay, I will have to see it. I think I'm going to dread it because I just hate movies where I know people are going to die at the end of the movie because. Based on what I've seen in the trailer. Oh, no, don't spoil it. Don't spoil it. No, this isn't a spoiler. I'm simply saying, from what I've seen in the trailer, there is no scientifically plausible way they could possibly survive at the end of the movie.
Yeah.
And so it feels like it's going to be one of these, like, open water movies where you sit for 90 minutes and then they just die in the end. And I just...
That might be why I don't want to see that movie because I remember when Open Water came out and I thought to myself, I would rather die by means of open water than see the movie Open Water.
I think I agree with you. Yes, Gravity, I'm going to have to see it because I want to see. I mean, it looks like they will have done one of the most plausible, near Earth orbit scenarios I've ever seen in a movie.
It looks cool.
And it's just going to be like an excruciating 2 hours of like, you can't possibly survive. Or if they survive, it's going to feel really Hollywood if they survive. And I don't think that director does Hollywood.
Okay. Well, and you know what? Maybe I could watch it on fast forward. There was a time when I was going to watch all of the AFI 100 movies. And then if I didn't like them, like if they were too slow or if there was trouble, I made a silent commitment that I was willing to fast forward through, Citizen Kane. And get this, I put in Citizen Kane, did not have to fast forward. Turns out there's a reason why it's one of the top 100 movies of the world, because it's fascinating. Anyway, so favorite science art pieces of yours. What are those? What are what
did I actually write there? Right. So the other side of my job, though, isn't actually taking data and finding ways of visualizing it, but it's actually getting to create artwork to help explain science as well.
Oh.
So I do get to wear both the art hat and the science hat quite literally in it. And the science illustration part has actually become one of the most enjoyable and gratifying things I've done for a while, because there are some results that we have where, we're putting out a press release and we want to get people interested in what we're doing, but the data it's based on is too visually uninteresting or too difficult to understand visually, that it would mean nothing if we put the data, and so there'd be nothing to draw people in.
Okay.
That's a point at which in science communication we want to switch over and do an illustration to try to help communicate what's interesting about what you're about to read.
Right.
So the artwork, this opportunity to do art that's motivated by science but ultimately has to be exciting and visual, because we have a very sophisticated audience with movies like Star Trek and Avengers and what they expect to see, right? You have to show stuff to get them excited to want to know what it's about.
Right.
So if we have a study about the discovery of an exoplanet around another world, and we think it's interesting because of its temperature or location, we think it might have clouds. We got to show a really cool looking visualization of a possible planet, with an interesting cloud cover.
Okay.
And that catches people's attention.
Yeah.
And it also sets them up so that when they go in to read the story, they're sort of preloaded with what it's about.
Okay.
So it's been really exciting. We've gotten a chance to do a lot of the work for the Kepler mission on their exciting discoveries. Sadly, the mission that's lost its flywheel, so it can't really do the same exoplanet work anymore.
What's the Kepler mission?
Oh, sorry. So the Kepler mission is actually also an LA-based band, as it turns out, but is also a NASA mission to study a patch of sky in incredible detail, looking at like 100,000 stars and looking for the faint hint of planets caused when the planets, which happen to be in the line of sight between us and the star, pass in front of the star and slightly reduce the total amount of light. So we're basically looking for these planetary transits, these little kind of
just like proof that there's
micro
a planet.
Eclipses that occur in front of these stars. We can't see the star surface, but we can detect this minute, like 0.5% dip in the amount of light when the planet moves in front.
Okay.
And if it happens
And the
again
Kepler
and again,
would just look at that one patch of the sky.
yeah, and just study
forever.
the same stars over and over and over again. Now it's lost a flywheel, so it can't. It's I forget exactly. It's several years into the mission now, so we still have a huge data set to study of what we've got from Kepler, but sadly it won't continue on that mission. But
Because
Spitzer has actually worked to back up Kepler, because once you have established a planet in the visible light, you actually can learn a lot by reobserving it in the infrared.
Okay.
Sometimes you can see the light from the planet. So Kepler's good at detecting the point at which the planet moves in front of the star. Sometimes Spitzer can detect the point at which the planet moves behind the star. And the little dip of light, in the infrared, sometimes the planet proportionally is much brighter than, the ratio is better from the light of the planet to the star. So you can actually see that dip. So you can actually measure exactly how bright the planet is in the infrared.
Okay.
Then you can start to piece together things like how hot the planet is.
Or how big it might be.
How big. Well, you get the big from the when the planet moves in front of the star.
Okay.
But then again, each piece gives you a different.
I'm adorable with my speculative science.
You start synthesizing it, and you can actually really start to add together how big the planet is. You can actually figure out the surface temperature. You can actually start to figure out things about winds. If the bright spot of the planet lines up with the star, if it's rotated, there might be winds blowing things around. A lot of cool stuff. But then, again, the data for that is very, very dull series of dots. Very subtle signals that even scientists have to hunt for.
All it is a blink. So what you do is you create an art image that makes that understandable, like you just explained to me.
Right. But probably the most wonderful piece I've got to work on was with a colleague, Bob Benjamin, who's been sort of synthesizing a lot of the study on the shape of our own galaxy.
Okay.
And which is actually really hard to figure out, right? We know so much more about what Andromeda looks like, or M83, or
those are galaxies.
Those
right?
are galaxies,
Got
right?
It.
Because we're outside of them and we get to look back into them and we see what it is.
Makes sense.
Our Milky Way has roughly the proportions of a compact disk. It's very thin, very wide, and we live smack in the middle, like a third out from the center.
Right.
And we're trying to figure out what this galaxy looks like if you could move above it by trying to piece out everything just crammed together. It's like being dropped down into the middle of Manhattan and say, okay, show me a map of the entire island of Manhattan just from where you happen to be standing in Times Square.
Right, by looking up at the sky.
Yeah, well, no, by looking out through the building, there are buildings in the way. I mean, you can see, the near streets, right? Yeah. You get that, the near stuff, you get pretty well. Then you start running into buildings that block your view of what's behind it,
right? And
then you have to kind of start guessing, and then like, well, you could use infrared, but then it's all like smushed on top of each other. And how far away is that distant building? I mean,
impossible.
That building's taller. Is it a taller building that's further away or a shorter building that's nearby? It might kind of look the same. So it's a really challenging task. So, astronomers have been hammering this for a century, trying to figure out. And Bob's been doing a lot of work in the infrared and doing counts of stars in different directions that let us tease out things like there's a bar that runs through the middle of our galaxy. Not, there is probably a little bit of alcohol in it, but not the
not a dance bar.
Not the bad pickup line kind of bar. It's actually stars that kind of line up in just a straight linear structure.
Like an axle.
Like an axle, yeah.
Yes.
And being able to refine where it is just by doing subtle statistics on counting the numbers of stars in different directions of the sky.
Okay.
Or studying or radio astronomers looking at gas clouds throughout the sky and looking at their relative velocities and being able to apply models and invert that out and figure out where the clumps of gas are and where the spiral arms in the galaxy are.
Right.
So a few years ago, I got a chance to work with Bob kind of collecting together the best of what's known at the time to make a roadmap to the Milky Way, basically. Sort of a top-down view of our best understanding of what the galaxy looks like from above.
Right.
But it was a piece of art, so it had to be a complete visual. So I took, I would look at pictures of other galaxies as a motivator of what galaxies kind of look like. Right. Then we would compare radio maps and precise measurements that are made to certain known star clusters or star-forming regions, and overlay that, and then overlay what we know about the bar from star counts, and overlay what we know about which arms have good overdensities of star counts in certain directions on sight lines, and you sort of lay all these pieces out, and you start trying to piece together, okay, this is what we think the best view is. where we don't know it, then we just sort of fill it in with, symmetry. Like, well, we know there's an arm over here, so let's go ahead and put another arm over there to match it,
Right, and we know what these other galaxies look like.
And we know what these other galaxies look like, and so you kind of motivate. So there was a lot of sort of equal parts of artistic synthesis and scientific like diagramming and distant scales are off, so you have to decide on the scale and make it all match that.
And then are you creating the art that goes with essentially his paper?
It was with a press release.
Okay,
but that particular piece of art now has gotten picked up and run everywhere because no one had really done a solid attempt to do this in a long time. Well, really ever, not with this kind of approach.
Right.
And just getting the idea that the Milky Way is a barred galaxy was kind of, even to museums was a new idea, even though we've sort of known this scientifically since the early 90s. But what's happened is then that piece of artwork has actually now, in 3 different occasions, matched scientific discoveries.
No.
Probably
like hell of a guess, Robert Hurt.
Like
nice work, man.
The most exciting one. A couple of them were kind of obvious. There was a symmetry. We knew that there was like this near feature, and let's assume there's one or the other. Probably the most exciting one was it's very hard. The farther out in the galaxy it is, the harder it is. So the far side of the galaxy, the data is kind of sketchy, and we were sort of filling out. We knew there was a part of an outer arm there that we filled in. And then we knew on the near side of the galaxy there was an arm that sort of swung out. And I sort of got to this point where it's like, okay, well, by symmetry, it looks like there ought to be more of an arm here. And so I sort of made an artistic choice of where the outer arm should fall and laid it out. Like 2 years later, I actually got an email from another scientist, Thomas Dame, who actually studies a lot of radio maps of gas in the galaxy.
Okay.
And he was in the process of publishing a new paper on the faint detection of this outer spiral arm.
Yeah.
And he wanted to know what data sets I had access to, because where I put that arm exactly matched not the location and the length of the data he found by studying the hydrogen gas out there. And he was like, were you working with some other data set?
Yeah.
And I just sort of, no, I just,
we
knew
stuff.
A part of it.
Yeah.
And then I really just looked at the other arm and I'm just like, well, I just made kind of a symmetry argument. Right. And sometimes that artistic balance actually presaged what came from the science.
And it genuinely, when you think about art, the link between art and science, it makes so much sense. Just because art is, if you look at Michelangelo, the perspective, and I have studied a small amount of art, so, but it's always about perspective. It's always about symmetry. It's always about trying to make things fit and look right when you do realistic, right? Mm-hmm. So why wouldn't that make so much sense of the science? But it's a hell of a guess, man. Yeah. That is awesome. Well,
it's, nature is filled with symmetries.
Right.
And art plays off of symmetry. And so the idea of filling in parts you don't know via symmetry, it was very flattering. Bob Benjamin had an invited lecture at one of the American Astronomical Society meetings a couple of years ago on the Milky Way structure. And when he showed the artwork, he actually proposed this to the community as not a piece of artwork or visualization, but as a scientific model.
Wow.
That, the idea that there is a kind of model you can approach where we don't, even areas we don't have data, to project that using things like symmetry arguments, that is as much a valid model as something that's from a different kind of rigorous math.
Yeah.
And the fact that the artwork has actually been, reconfirmed several times, that kind of validates it to the level of being more than art. So somewhere, not just art, right? It is where the
scientific
science.
Model.
Yeah.
What's the name of that piece of art?
Probably if you just Google roadmap to the Milky Way, you'd find it. It's on the Spitzer.
I will link that up.
Yeah, it's on the Spitzer website. So
that is awesome. So, is there now? We're getting close here to an hour. It's almost over immediately. That's the way of the Dork Forest. You start talking about the thing you know, the thing you love, and then an hour goes by almost immediately.
Of course it does.
So, but what is Deep Impact Recipe? And what is New Star Black Hole?
Oh, that's right. Yes, just a few other fun visualizations we did that were not data-based, but
art-based.
Art-based, how to approach something. The Deep Impact was a mission that NASA sent out. It actually recently in fact, they just announced this week that they lost contact with the probe. But
Okay.
its primary mission was of a resounding success. It actually rendezvoused with the comet and dropped off an impactor that slammed into the comet going hundreds of miles an hour.
Okay.
And in the process, kicked up a plume of material that spewed out of the comet that Deep Impact and then telescopes all over the Earth and in space all observed to understand what is a comet made up out of.
Yeah.
And the idea is, when we see a comet, we only see the stuff on the outside and stuff that gets blown off. Our idea was, well, let's actually just blow it up.
Right.
And look at all the stuff that gets kicked out of the inside. So,
right.
It's like dissecting someone to, and Spitzer's contribution was we had infrared spectroscopy of that material. We took the light in the infrared, broke it up into its constituent wavelengths, and we made it. We plotted a squiggly little line graph, but each component, each mineral, each molecule has unique fingerprints in light that it emits, that certain wavelengths that each one.
Oh.
And so by looking at these squiggly lines and where little peaks show up, you can actually reverse
Tell what
engineer and
it's
figure out what it's made of.
Oh.
And so from
Science is
Spitzer,
cool.
we were able to combining the Spitzer data with ground-based data, we were able to get a very good recipe for how you make a comet. All the different minerals and, carbon monoxide and water we knew about, but specific kinds of minerals and compounds and proportions. So we wanted to come up with a way of making this little squiggly line exciting for our press release. And we realized what's more interesting than the squiggly line is what it told us about the components. We actually came up with this idea of making a photograph of all the things that go in to make a comet done up like a cooking recipe.
Yeah.
And so we called up the geology department next door and said, hey, would you be willing to give us all these minerals for a photo shoot? So, oh yeah, come on over.
Oh.
So we went through, so we had the laundry list of these are all the things Deep Impact found. They took us through, they had this wonderful little room filled with little drawers and little Jevonite minerals here and little crystalline particles here. And we just scooped it all up into little measuring spoons and had a cup of dry ice and a cup of regular ice. Sure. And
did you
my
have
colleague,
the proportions?
We didn't do the proportions.
Sure, you do what you can.
Do what you can. We wanted it visible, enough to be visible on all the pieces. And my colleague Tim Pyle, who's an artist, who sort of artist interested in science, counterpart to a scientist interested in art that I am, actually made up a little menu card, like a page out of a recipe book, with all the ingredients listed, and we arranged that all together and made a photo of it. Neat. And that was actually a really popular way of showing the constituents of a comet. And,
that's awesome. I have a question. Is it everything that makes up a comet? Is it do we have it on Earth?
Yes.
Okay.
Yeah, everything that we detected we have on Earth. So
the universe seems to be made up of the same stuff.
Very much so. Well, in fact, that makes a lot of sense because we actually think that the way we got a lot of the organic materials and the things like water on the Earth after it formed was that it was actually delivered here by comets.
Okay.
There were a lot more comets in the early solar system. They're the debris left over from the formation of the planets. They're the stuff that formed further out, was colder, was icy, and collected, but it's all being kicked up and stirred in and every time something gets kicked in the inner system, there's a chance of slam into the Earth.
Okay.
When there's more stuff flying around the solar system, there's a lot more impacts going on.
Okay.
So we actually think comets are like a kind of preserved petri dish of the stuff that actually got dumped onto the surface of the early Earth after it cooled and was forming, and became where we got our carbon dioxide and our water, and maybe even some of the organic material constituents that led to the life.
Yeah. Oh, that's awesome. Cool. And what's a new star black hole?
Oh, and another one was NuSTAR is a new X-ray observatory that Caltech has launched funded by NASA to study the hard X-rays, the highest energy X-rays.
Okay.
And their images are very kind of fuzzy, but they actually can make images out of hard X-rays. But again, what's interesting, what they deduce out of those images. And they had a really amazing result, which is just mind-blowing, trying to deduce the idea that black holes, which are these collections of mass so dense that nothing can escape, they're basically singularities of gravity that we know exist at the centers of galaxies that
Wait,
that you can't see
hole
into.
Is a thing?
It's a thing.
It's not a hole?
It's a hole in the fabric of space-time caused by a collection of mass so dense that there is only a path in. There is not a path out.
Okay.
And so light, material, everything that
Right.
goes in is just in forever. The only possible directions are down.
Okay.
There are no up once you get past a certain threshold.
Right, but it's made of something.
But it was probably...
And it collects things.
And it collects things. And
All
things
right.
can fall into it, and then it gets bigger.
And then it just gets bigger.
Yes. And we think the core of every galaxy has a supermassive black hole of, millions of times more massive than the sun.
Okay.
And
Just holding on to everything
but we don't
else.
we can't see them, but we can see how they affect other things.
Oh.
Like in our own solar system, in our own galaxy, in our
Right.
Milky Way, we actually can look using infrared light into the core of our galaxy and see the very brightest stars. And we look at them, month after month, year after year, and we can actually see stars. I mean, whole stars bigger than the sun, orbiting something we can't see. Several of them we've been doing this since the 90s. Andrea Ghez at UCLA is actually one of the leaders of this effort. So she's gone back year after year and tracked the stars in the center of our galaxy.
They're
They
circling
move,
something.
and they move. Now, seeing something move in our lifetimes is amazing in astronomy. Seeing it move month to month is astonishing, especially when it's something as huge as a star.
And
Right.
wow.
Even the nearby stars, year to year, are only moving, like tiny fractions, and we're very close to them. This thing is like,
bazillion
thousands of light years away. But by doing so, you basically can calculate. Like we know we know how far away it is.
Right.
We've measured its path. You can calculate how much mass has to be there in order to cause a star to orbit
that
like
we
that.
are not seeing, that we cannot see.
Right. And you do something on the order of like several million times the mass of our own sun, and there's nothing we can see there. And so you figure out the only thing in physics we have to explain that is a black hole.
All right.
In other galaxies, there is a lot more material in the centers of the galaxy than just stars. There's gas and dust. And again, if there's a black hole there, that stuff is all going to get spun up into a disk that's rotating around it. And as it the friction, the viscosity of the disk causes drag that causes it to eventually drop down, fall into the black hole, feeding the black hole, making the black hole bigger. And we can see the disk. We can't see the black hole, but we can
Right.
see these
Right,
disks.
the thing's heading towards it.
And so what NuSTAR did was it looked at a spinning disk around a black hole in a nearby galaxy, and it measured very precisely the hard X-ray spectrum.
Okay.
And it saw sort of a weird feature in that spectrum that indicated that this disk had a basically the light was being changed from the disk by the black hole a little bit, and it's very complex models, but what it boils down to is there's this weird thing that you can do in the math. Even though this black hole doesn't really have a physical surface,
Yeah.
it can still have a rotation. And the rotation has the only effect the rotation has is through general relativity on how it redshifts, the way it changes. Like you look on one side of the black hole and light moves differently around one side than the other.
You got to look close.
You got to
is
look
what
close.
You're saying.
And so even this thing is like tiny. I mean, the actual surface of the black hole, or the
thing that you could-
the edge of the event horizon,
Yeah.
is like way smaller than the inner solar system. And in this is a galaxy, millions of light years away. By studying the way the X-ray light is distorted in that area, and the way light is reflecting off of that disk in the X-rays, and how it changes the shape of the line, they can actually deduce the black hole is spinning at what they can call a critical level. It's sort of the fastest rotation the black hole could theoretically have,
Right.
based on the disk. And it's like weird, mind-numbing stuff, all from like a squiggly line.
Yeah.
But then getting a chance to do sort of the
You had to do-
canonical what the disk would look like around
Yeah.
the black hole illustration for that was phenomenal. And reddening one side and brightening up another, and trying to fold in a little bit of relativity into that diagram
Yeah.
to help sort of set up that story was, again, one of the more interesting pieces I've had to work on.
So cool. So cool. All right. We're at an hour, but I want to know what the Babylon 5 connection is.
Oh, the Babylon 5 connection.
Because we
of
could,
course.
with the Robert Hurt, you can always just do a Babylon 5 episode. You can do a Star Trek episode. You can do
my
some gaming.
Starship collection
Your
episode.
Starship collection. I actually, lot of people can talk to me about Babylon 5 and Star Trek. I don't know a lot of people that can talk to me about their Starship collection.
I am a connoisseur of starships.
Sure.
I know a lot about that.
We'll have you back.
No, so obviously there's a lot of sci-fi love in the office.
Sure.
And Tim Pyle, I mentioned, is also a big Babylon 5 fan and Star Trek fan. And
yeah.
we always have our little geek debriefs, when we're working on projects. But we did have one press release some years ago that involved studying the properties of a disk of debris around the star Epsilon Eridani.
Okay.
And true sci-fi aficionados may know that that's a very special star system for many ways. It's one of two proposed locations of Vulcan.
Oh, really?
Though in the soft canon, it's the less favored location of Vulcan than the other system. But it is also well established in canon as the home of the Babylon 5 station around that orbits Epsilon 3, which is would be the third planet in the Epsilon Eridani system. And since we were doing this visualization of this system, and Tim and I are both big Babylon 5 fans, we sort of thought we should put some little homage into that. And so Tim actually was doing the art for that one, but we talked about it and we came up with, if you look at that piece of art very carefully and you study one of the nebulae near the planet, if you look very carefully, you will see the faint silhouette of something that looks vaguely spider-like. To a Babylon 5 fan, you would recognize it as the silhouette of the shadow vessel.
The
floating
shadow
off
vessel. I've never watched that show. Tamara Boyd used to take me to task about it.
Well, I will too. It's a classic.
But I did have as an acting teacher once Carrie Dobro.
Carrie Dobro is wonderful. She was, of course, in Crusade. She was is it a spin-off? The spin-off series of Babylon 5 was Crusade.
Was she in the original Babylon 5 too, or no?
She might have done a guest role, but I'm not sure. But she was a regular. She was like
one of the leads, ensemble leads
on Crusade.
Okay, and hilarious. Holy crap, she was a funny woman.
And she was one of the leads in a little-known sci-fi Saturday morning show called Hypernauts.
Hypernauts.
Yes.
Animated or
live action?
Live action.
She played an alien in Hypernauts.
Excellent.
Very cheesy, but she was really good in it. She was the best part of the show.
She exudes charm like a faucet. She was and was a great teacher. So
nice.
Robert Hurt.
I should go on record though. To date, that is the only sci-fi Easter egg we've ever put in a piece of art, and we hit it there. To my knowledge, no one ever independently discovered it, but we did kind of announce it publicly in a couple interviews we did on Science Viz. And at one point or another, somebody on Facebook, the Babylon 5 Facebook group actually stumbled across the reference to it, dug it up, and actually put a little post there, got a lot of commentary, and really pissed off one guy that we got this really bitter letter in the office about NASA should fire anyone who wastes public funds.
Frickin' Bossy Magoo.
The funny thing is, everything got smooth. We wrote back a very clean response to the guy and pointed out that the actual press release mentioned Babylon 5 because when we were setting it up, we actually said, this system is well known in science fiction. We just pointed out it was not intended to deceive. It's very different. Like if I had gone and I'd taken an image from Spitzer, like data, and faked something in there. Oh God, the conspiracy theorists would be all over that.
Right.
That we do not do. That we do not do. Right. We will go in and we will clean up artifacts in images because, like any camera, there are flaws that will happen. A bright object can create sort of the equivalent of lens flares, which look like physical objects, but they're not. So
you can tell because they're in every image.
Right, they're in every image. There are a lot of well-characterized effects that occur that we know are not physical objects. And that is one thing we will do as in general on all the telescope facilities. We'll do this. We'll clean up artifacts that could be mistaken as actual objects that aren't.
Right.
And
look, it's God. And
right. It's funny.
He's flying by that black hole. That seems unlikely.
Yeah. In fact, one time we released the same image a couple times over a few years, and the first image I didn't have time to work on, And when I did, I went back and I cleaned it up a little more. And someone actually within a week or within a couple of days wrote back, "Oh, I noticed there's a difference. There's a skull-shaped object that was in this one image, not the other. Could that have been a planet that was passing through?" Everyone loves, it's mind-numbing. People actually
They want so much.
They want to find those things. And
yeah, I want it too. But
sadly,
we all want it.
Planets and asteroids, they're pretty hard to find. They don't look very interesting. And if it looks really cool, it's probably a detector error.
Dust. It might be a scratch. We're very sorry. Oh my God, this was the greatest episode. Thank you so much, Robert.
Oh, I'm sure you say that to all of your nerds.
I say it to a lot of them, and you're one of them. For the love of God, Robert Hurt, that was awesome. Thank you so much for being on the show.
It's been a pleasure.
Well, that show was awesome. Let's do the credits. Patrick Brady, he fixes the audio every week. He also does the teaser videos on YouTube. So Patrick Brady is an awesome guy, and I thank him for his work. Mike Rickberg sang the song you heard at the beginning, composed and sang it with his girlfriend Sarah. He's going to sing in about a heartbeat for the Mexican Hat Dance. And Vilmos fixes my website, JackieCation.com. So support him and his work. Thanks a lot, you guys. Take care out there. Bye.
My hat, my hat, my hat. They're dancing around my hat. My hat, my hat, my hat. Well, what do you think of that? If it looks like a Mexican hat dance and it sounds like a Mexican hat dance, it's most likely a Mexican hat dance. So take off your hat and let's dance.
Yay! Oh my God. Why don't we just call that as the end of the show?